So thank you everyone for joining us for this week's Etro U session. This is an introductory course, as it were, to what you need to know about building systems, especially HVAC. It is run by our MEP manager, Ben Brower, and he will take us through some of the basics that we need to know about when it comes to our mechanical systems in our buildings and what it means when we hear the short-term abbreviations of the system names. Thanks, Ben.
Great. Well, thanks everyone for joining. As Karina said, this is the first of several HVAC learning sessions. I'm going to go through primarily three major mechanical systems. Tropa showed this sketch to us, and I think it's a very good representation of the history of mechanical systems. In my career, I've been fortunate to see the tail end of that middle house diagram, let's call it, the tail end of the 20th century era of massively complex mechanical plant systems. We're now sort of entering an era of more mechanical simplification with the step code, passive house, net zero, etc. However, we'll still see and continue building TIs and buildings with these more complicated, older style mechanical systems. This presentation will concentrate on somewhat basic knowledge of the three major types of mechanical systems: VAV, fan coil, and VRF, or VRV, some people call them. I'll show you three examples of past projects I've worked on, and future M&E Etro sessions will get into more complicated hybrid systems and more specific elements that we as constructors should know. First off, we will go through some of the few HVAC terms that we should familiar ourselves with. HVAC simply is heating, ventilation, and air conditioning. I'm going to start fairly basic because we do have some younger and some new people to the industry. Ventilation is generally referred to as fresh air, and the percentages are dictated by ASHRAE. For those that don't know ASHRAE, ASHRAE is American Society of Heating, Refrigeration, and Air Conditioning. Heat exchangers are devices for the transfer of heat energy from a source to a load medium, typically used to isolate an open system, i.e. a loop which is open to atmosphere, or another element such as ocean water. Cooling towers are an example of this. Closed systems or a closed loop is, for instance, a glycol system. And we utilize heat exchangers to transfer heat or lack of heat from one of those systems to another. BTUs are a unit of measuring energy, British thermal units, unit of measurement for heating and cooling. 12,000 BTUs is equal to 1 ton. So if you hear, it's 1 ton of cooling, it equals 12,000 BTUs. AHUs are simply air handling units, a box, often a very large box with a fan. Rooftop units, any mechanical device or piece of equipment that's on a roof can be called a rooftop unit. Often rooftop units and air handling units are used interchangeably, but a rooftop unit could be a condensing unit, it could be a fan simply placed on the roof. Split system is generally referred to as DX, or direct expansion air conditioning system, which utilizes refrigerant, not water. Heat pumps is a split system or DX system that can heat and cool. And then VFDs and VFDs are variable speed drives. You'll hear those quite often in the industry. It's a piece of equipment that regulates the speed and rotation force of an electric motor. Essentially, it's a speed control device for motors and fans. Often safe, well, most often to save energy in the building. This presentation, we will touch on the three major systems, as I said, VAV, fan coil, and VRF. The one element in common with all three mechanical systems are air handling units. In general, air handling units are used to provide fresh air to the occupants of a building. Without fresh air, people get grumpy. On the left side is a schematic for a 100% fresh air system, and you'll only see these generally in environments such as Vancouver, fairly temperate areas of the world. And the reason for which is it takes a lot of energy to heat or cool. If there's big swings of outdoor air temperature or a big requirement for cooling, big requirement for heating, i.e. extreme south or extreme northern areas of the world, you won't see 100% outdoor air units or free air conditioning units very often. On the right is a schematic of a much more commonly used air handling unit, which is a mixed air handling unit. These are much commonly seen around the world and recycle some of the already conditioned air within a building back to the occupants. Because it's already been preconditioned with heating and cooling, means that the system is more energy efficient overall. However, you do run into issues, for instance, our pandemic here, COVID. Often we're adding more filtration to that recycled air now because we are worried about contaminants of the recycled air back into the system. Now we'll start looking at the first of the three mechanical systems, VAVs. In general, you don't see these very often anymore. In general, moving energy around the building with air is much less efficient than using water or refrigerant. For those maybe doing TIs in older buildings, might come across a VAV system, which often entails a massive ring duct. Thermal control is achieved by controlling the amount of air, not the flow of water, for instance, in a fan coil, to occupied zones through what is called a variable air volume box, which you'll see there in the description in the diagrams. Here is one example of the VAV system. This is a plant diagram for Hvac Fairview I did at 725 Granville Street, where Nordstrom's is or was. I'm not sure if they've closed down quite yet. Located upstairs is Sony ImageWorks and Microsoft on the upper floors. This is the diagram of the major plants. You'll see in the top corner is cooling towers and chillers. Bottom left is an example of a heat exchanger. That's a water-to-water heat exchanger. In the middle there, those big red objects are pumps. That's the triplex pump system. And in the top right corner is a steam-to-water heat exchanger. Due to this project being on district energy, the creative energy system, they still have steam there. They're talking about converting that to hot water maybe in the future, but right now it's steam. And it's quite of the VAV systems, it's quite an elegant one, quite energy efficient, but still not quite as energy efficient as the two other systems that we'll be discussing here. Next system we'll talk about, which is the most common, is fan coils. The term fan coils can be used to describe both hydronic or refrigeration type fan coils, but for the purpose of this presentation, we'll use the term fan coil to describe the hydronic type, i.e. water. Fan coils are exactly what they sound like, boxes with fans and coils. Fan coils can be used for heating or cooling, or both. In the event the fan coil is used for heating or cooling, we refer to them as two-pipe fan coils. In the event the fan coil is used for both heating and cooling, we normally refer to them as four-pipe fan coils. I'm going to complicate that a little bit. Some of you may have heard of a technology called six-way valves, which is coming out or has been out for a few years now. Six-way valves are a very cost-effective solution to utilize a two-pipe fan coil for both heating and cooling. For those that want to know more about six-way valve, I'm not going to go into too much detail on six-way valves, sorry, here, but for those that want to know more, please come by my desk or shoot me an email. I can describe better how six-way fan coil assemblies work. And for those that want to impress our clients, their six-way valve assemblies are often a very good VE solution that impresses our clients, should the engineer still be designing with four-pipe fan coils. This is a diagram. This is the first plant diagram for Grosvenor at the Ambleside Residences in West Vancouver, and is an example of a four-pipe fan coil plant. To this day, this is probably the most elegant and efficient mechanical system I've ever worked on. Unfortunately, this mechanical system was redesigned to a VRF system, which I still think to this day was a big mistake. But at the time, the owner wanted to realize about $100 million in capital savings, which they did, but has since probably incurred more than $1 million in additional operating costs, which is quite unfortunate. But As I said, that's a good example of a fan coil, a very, very efficient fan coil plant. The last mechanical system we're going to discuss is the variable refrigerants, or VRF systems. VRF is a proprietary term actually reserved for Mitsubishi VRF systems, or multi-slit units. VRV is commonly used for VRV is commonly used for Daikin, LG, Samsung, and others. But the family of mechanical systems, let's call it, are most commonly referred to as VRF. VRF is the family of mechanical heat pump systems that utilize one outdoor unit for several indoor units, or multi-split systems. VR systems are 100% refrigeration, not to be confused with water systems. That means no water is being pumped to the fan coils, only refrigerant in the form of refrigerant liquid or refrigerant vapor. VRF pros and cons are listed there. Generally speaking, the pros are lower capital costs. As I said before with the Ambleside example, energy efficient costs are higher, i.e. energy costs lower. Individual temperature control, often you see many more zones which give occupants or offices or suites more temperature controls of their environments. The major cons are specialized mechanical technicians, is what the Ambleside realized moving forward. They need to hire refrigeration technicians, which is a premium operating cost, versus any plumber can work on a fan coil system, for instance. The controls are proprietary, i.e. you have to use Mitsubishi controls with a Mitsubishi system, or Daikin controls with Daikin system, et cetera, et cetera. You can't tie in the ESC Delta into a Mitsubishi system. Well, you can certain other elements, but not for the occupant temperature control, for instance. If you've got any sort of smart building systems and you want to integrate, for instance, elevator occupancy, lighting control, automated curtains, and that sort of thing into the system, it's very difficult to do with VRF systems. It's much easier to do with a more generic control systems like Delta or control solutions and such. There's no heating, cooling redundancy like there can be with fan coils. CSA B52 refrigeration code restricts the amount of refrigeration that can go into the building due to the weight of refrigerant is heavier than air, and there is a slim possibility of occupant suffocation. So looking at B52, you really have to be concerned at the refrigeration loads of a building, air seals of the building, where that refrigeration is mainly located in a building. It's a bit of a design, a finicky design element that you have to be concerned about. There will be higher electrical install costs due to generally bigger feeders. And typically mechanical rooms have to be sporadically located throughout the building instead of having one massive plant room, which can be both a pro and a con depending on the architect you talk to. Here is an example of VRF system. This is the MNP tower at 1021 West Hastings. Engineers, just by the way, generally love working on these systems because they don't actually produce these system schematics themselves. These are done by the VRF suppliers, and the engineer gets away with charging the same design fees as if they did the design themselves. It's a pretty slick system in this case, but every floor required a mechanical room to place those outdoor units, which you see in the kind of top left corner and middle left there. But they did save, they were able to achieve one more level of tenant occupancy space because they didn't have a plant room per se for the major mechanical equipment such as chillers and boilers and such. And that kind of wraps me up. That's faster than I thought. My last slide here is, I thought I'd throw this 3D model in there as a last slide. This is the district energy plant at Marine Gateway, which might give you an example of how complicated some of these systems get. This is the district energy plant for well over 1 million square feet of residences and commercial space. 4-pipe fan coil primarily. It's pre-slick system. It's got some ground source elements to it as well. It was actually one of my first BIM projects, a full 300, well, 300 plus anyway. No prefab elements, or not much of the way prefab elements yet, so we didn't take it to LOD 400. And we'll talk about, I'm sure that for those that don't know what I'm talking about, BIM and LODs and whatnot, I'm sure there's plenty to give you a lunch and learn from our virtual construction side, but essentially that's the level of detail that the 3D models get up to for purposes of design coordination or prefabrication that some of the mechanical trades or architectural elements can be utilized for. Any questions? Oh, I can't see. Apologies, I don't know how to use the system, but I think there's probably some hands up.
I'll pick a name. So go ahead, Vin.
I think Shane has his hand up first. Go ahead, Shane.
Oh, you're too kind. Hey, Ben, I was wondering, could you go back to the slide with the 6-valve system? Just curious to know, like, if this is a VE item that, pre-con may be suggesting in the future to reduce cost to the owner, how much additional ceiling space here is required to a typical, installation?
Very good question. Typically, we're talking like a 2-ton, 2.5-ton, maybe 3-ton for residence or typical commercial office space. The assembly, if you're looking at prefab assembly, it can be quite large. If the mechanical trade is to assemble that with threaded pipe, 6-way valve, the strainers, the pick V's and that sort of thing, they can get to the one I did for Amazon Post. They were probably 3 feet by 3 feet by a foot or so in depth.
Gotcha.
However, there are some companies, for instance, GE Camini has a very, very slick prefabricated, precast, all in a neat little bundle you can order from Italy, and that shrinks down to about 2 feet by 1 feet by 6 inches.
Okay, cool.
Yeah.
Thank you very much.
Yeah.
All right, Vin, it's your turn now.
Thanks. Ben, just for that VRF system, does it, I assume, beside cooling, does it also do heating or ventilation, or you need separate system for that?
Yes, it can be ordered with just cooling, but primarily it's utilized for both heating and cooling. And the nice thing about the system is utilizing what's called a BCU or brain control box. You can heat and cool at the same time, and in some cases exchange heat from one side of the building to provide free heating on the other side of the building, or vice versa with cooling.
That's pretty cool. But what about ventilation? Like, does it actually do ventilation, or do you actually have a separate system for ventilation?
No, ventilation's a separate system utilizing the makeup air units or air handling units that still have to be there to provide fresh air to the back of these fan coils. VRF fan coil, it's just a refrigeration version of the hydronic fan coil. They both require ventilation, a small duct providing fresh air to the back of the unit.
Got it. Thank you.
Yeah.
Go ahead, Abdullah.
Yeah, thanks, Ben, for the presentation. I just had a question regarding the your last slide just before the 3D model. You mentioned there that using the VRF system allowed you to save the space, basically not using the plant room, but instead you utilize the mechanical room in each level, if I understood well.
That's right.
Like, what's the mechanical room? Like, what did you use the mechanical room for at each level, and how big it is?
In this instance, the rooms were about 8 feet by 12 to 20, depending on the footprint. And in those mechanical rooms was one side was a giant louver for heat exhaust. And in those rooms were the commonly referred to as the condensing unit, but let's just call it the outdoor unit, which are if you see in the top left corner there, those are required to be outdoors. Or in an outdoor space that could reject the heat. And each floor required, I think in some instances, we did every other floor. So it was still a mechanical space per floor, but got away from having a massive or utilizing the entire top floor, for instance, as a mechanical room.
Do you usually go with this option, or because I don't know. I mean, I'm not really experienced with HVAC systems, but the way that I see it these days are just sticking to one giant, maybe air handling unit that will act as your outdoor unit and will be placed on the roof, and then everything else will be connected to it. Or is it something usual to have the mechanical room in each floor in such towers?
For a commercial tower, this was extremely rare. It's M&P is, I think, to this day, the only one in existence here in Vancouver. We may see VRF in a commercial application a little more often with the current step code, which is more electrically inclined. But it was sort of a unique case. It's more commonly in residential applications.
Okay, thank you.
And there are no more hands up, but if there are more questions, feel free to ask Ben. Go ahead, Shiva.
Hi, Ben. Yeah, thanks for the presentation. So would you say the FCU system is the best, with the downside being the cost?
I'm always a huge advocate for fan coils. It's the energy efficiency is way up there. The operating facility costs are lower than VRF. It's the tried and true method. It's the tank of mechanical systems. Very little could go wrong with them. Controls are easier. It's easier to modify for smarter building applications. Fan coils is definitely my preference on almost all instances.
Okay. And so can I say that like the first one, the VAV system is kind of obsolete nowadays?
VAV is somewhat obsolete. Yeah, you don't see those in new buildings. I'm going to say you'll never find those ever designed for a new building, but we'll still be doing lots of TIs in buildings that have those systems in them. Yeah, especially with today's cost of steel, it requires a lot of sheet metal, a lot of ductwork, and the cost of sheet metal is just astronomical right now. So we will probably never see a new building with VAV primary system in them ever again here in Vancouver. Yeah.
Okay. Thank you.
Yeah. Good. No more questions.
No more questions. Thank you very much, Ben.
Perfect. Good timing. All right. Thank you, everyone.
Have a good afternoon.
Cheers.
Thanks, Ben.